Okay, I think we'll go ahead and get started. Maybe a few more people will wander in eventually. So first I wanted to start with a thank you for everyone. This is going to be my final lecture, and it's been a lot of fun. And so I want to thank all the students and the TAs and Josh for making this a good experience. A little overwhelming on such a big class, although you wouldn't know it from the size of the audience today. But hello, all the webcast viewers. And then also next fall, I'll probably be teaching a graduate level course in audio signal processing. So I'm not sure if I'll see any of the same faces, but just to be aware that that class is available. So we'll go ahead and go on to our regular announcements. The Tuesday after Thanksgiving, we're going to have another guest lecture from one of the TAs on deep robotics. And then we have all our normal upcoming assignments. The dates have shifted around a little bit, and so do make a note of these dates. The homework is due on a Wednesday. The final we've moved back to the end of Dead Week to give you guys more time to work on it. We'll also be doing a daily updates of the contest scores, and so some opportunities for extra credit there. Project 6, part of it is out. We'll release the rest of it as it becomes available. The old one we were not happy with, so we tried to do a new one here. And then the final exam will be Tuesday, December 13th. It will cover everything in the class, including the special topics. And the special topic today is going to be speech recognition, and I say a CS188 perspective. And so if you haven't just taken CS188, some of this stuff may not be comprehensible, but I don't think there are too many people in the audience like that, so we'll see. And with apologies to Gary Larson, so this is speech recognition, that someone is talking and some agent is trying to listen, and maybe it hears the right things and maybe it doesn't. So the first question is, why is it hard? Why is this a problem that's worth addressing? And there are lots of reasons, but one of the first ones is that there's many different ways to say the same thing. So I can speak quietly or I can speak loudly, and the sound is different. You have different accents. You have gender, male, female, child. You have speaking style. You have speed, and so on and so forth. Let's see if I can find my mouse. And one way to demonstrate this is, in order to train speech recognition systems, we collect a lot of audio data, and we have people transcribe it. So we have a whole collection of meetings that we had in our own research group, and then we had someone write down every word that was spoken. So I just searched for something in that corpus to give you an example of the variety. So hopefully this will work.
Something.
So that was the first sort of 40 or so times where an annotator said the person said the word something. And think about all the different ways that was said when you were listening to it. So let's just play a little bit of it again, especially how many times someone might have just said something and things like that. And yet a person still understands it in context. So you can see how hard that can be, that there are lots of different ways of saying the same thing, and we're asking our machine learning system to recognize all of those as the word something. So another issue is word boundaries. Now, if you're listening to something in a language you are perceiving word boundaries. So I want you to listen carefully to this one and tell me, do you hear word boundaries in this phrase, in this sentence? Anyone? Does anyone hear word boundaries? No one here speaks Zulu? So if you spoke Zulu, you would hear word boundaries. But word boundaries are a function of our understanding. They don't actually exist in the audio stream. And so you can't say, as a first step, figure out where the words are, and as a second step, figure out what the words are. There are no word boundaries in actual audio. Now, there can be. You notice that speaker paused occasionally. Usually a pause is after a word. but it doesn't necessarily have to be after a word. So it gets very confusing when you have to do all this stuff. So this is another reason why it can be very hard to do speech recognition. So another reason is what's called homophony, that the same sounds may have many different meanings. And so take a look at this. So if you're not a native speaker of English, this may be difficult, but sort of sound it out to yourself, and what is this sentence actually saying? Right? How about that sentence, where I'm telling you that's not actually what the person said? Okay, so my number is 8182424, right? Yet I would want to write it down as it is in the red. And then recognize speech, that's an old example from IBM, where what the person really said is recognize speech. And if you think about that, that's just sort of a different way of segmenting up the words. So it becomes very hard if you actually want to get what the person said. So other effects are sort of the acoustic effects. So we have normal background noise. We all notice that when they're doing the construction outside, it becomes difficult to understand. There's something called reverberation, which is basically echo. So when I'm talking, my voice goes from my mouth to your ear directly. But it also bounces off the ceiling and goes to your ear. It also bounces off the back wall and goes to your ear. And so all of those sort of are delayed copies, delayed echoes of the original sound. And humans just process that out. We're not even generally aware of it if you're not thinking about it. Then you have channel effects. If you take someone who's never spoken on a telephone before and you put them on the telephone, they'll have a hard time understanding what's spoken. And that's because the way it's broadcast introduces other effects. That it's just different if you're talking through various microphones than if you're talking directly. So here's an example of what's called the cocktail party problem, where there's lots of people talking in the background. There is a foreground speaker, so listen carefully and see if you can hear what the foreground speaker is saying. Oops. Or you can look at a picture of a cow. Anyone? Did you get anything from the foreground speaker? Let's listen again. I think Arlo, who is, I work for him currently, may be the only person in the room who had any chance of getting it. I keep doing that. One more try. So here's with the babble. Yeah, you got it. Yep, it's a timid sentence. So here's without the background. She had your dark suit in greasy wash water all year. I use this example because it's from a particular early speech recognition corpus called TIMIT, where people were carefully reading sentences that were phonetically balanced. In other words, it had about the same number of speech sounds in the sentence as opposed to normal English. But now let's listen to the clean one. Now listen to this again. Now suddenly you can hear it. I mean, that's pretty weird, right? And yet we're asking the speech recognizer, just as we did in the first time, for it to understand what the person said. And so, humans are incredibly good at speech, but there's a lot going on in the brain that's hard to process. So here's an example that I like to give to people who are vision researchers who don't understand why speech is so hard, or audio in general. So here's a vision processing problem. What is that? Well, it's a cow, right? This is equivalent to you have clean audio, no background noise. There's one speaker, and they said one word, cow. Pretty easy. But in speech, you have channel effects. So channel effects are sort of like lens aberrations in vision processing, where the channel changes what the signal looks like. Okay, in addition to channel effects, we have reverberation and echo, like I described before. And again, this is sort of like the same signal copied and pasted over it. Okay, so in addition to reverberation and echo, we have background noise. So we have another object, which is a perfectly valid audio object, but it's interfering with what you're trying to recognize, right? And we don't just have one background noise. We can have an infinite number of background noises. So the speech problem and the audio problem in general is more equivalent to this. We're asking you to look at this picture and say that's not Einstein, it's not a bird, it's not a coffee cup, it's a cow. And not only that, it's Bessie the cow. And I haven't even gotten into the fact that speech is a dynamic signal, that it changes over time. And so in fact, we have different cows appearing, different words as you speak. Sometimes the cow disappears and you only have the upside-down face of Einstein. So it gets to be a very, very difficult problem. So what I wanted to talk about first is just a little bit of history of speech recognition, just to see how far back it goes. So this is sort of a question goat. Think about what decade do you think the first consumer electronic speech recognition device came out, where you could go out and buy something that was a speech recognition device. In this case, it was a toy. Any guess on decade? Just shout it out. Anyone willing to take a guess so that I can say no, it's earlier? No, it's earlier. Anyone else so I can say no, it's earlier? No, it's earlier. Anyone else? Oh, you're actually closer than everyone else. So the actual answer where you could go out and buy one was a little toy called Radio Rex in 1922. And so there was no computers in 1922. This was a pure electronic device. And it actually responded to the sound in Rex. So when I say Rex, I'm saying in the middle of that. And that just turns out to have particular energy at a particular tone at 500 megahertz. And you can tune an electromagnet to respond to that frequency. And so when you said, come Rex, if you said the sound loud enough, it would release an electromagnet and it would jump out of his house. And that was in 1922. Now, 40 years before that, Edison built a prototype that was similar to this. It was a little sawmill that was doing the same thing. It wasn't consumer electronic. You couldn't buy it, but he did have one. And so that was in the 1880s. So we've been working on speech recognition for 130 years. That's how long it's taken to get to the point where we have the speech recognition on your phone and things like that. So I'm not going to talk about a lot of the history, but I do want to talk about a little bit that's relevant to this class, to the topics we've covered, which is basically that AI sort of grew up with speech recognition. Speech recognition grew up with artificial intelligence. So as better AI techniques came up, they were applied to speech recognition, and in fact, speech recognition was a big driver of it. So we talked earlier about expert systems. This was sort of very early in the AI world. And you would get an expert, a linguist in this case, and you would ask them, well, here's a sound, what's the word? And they would say, well, the tone is going up here, and there's a closure here, and, well, that's probably a T. And they would encode hundreds of these rules, or thousands of them. And you'd have a computer system that tried to put it all together. It was very fragile, and it really didn't work. And so there was this joke from Fred Jelinek that every time he fired a linguist, his speech recognizer got better. This was just in the time when we were transitioning from these expert systems to more statistical methods. So I love that quote. Next up came sort of nearest neighbor approaches. And in this approach, the early ones were just template matching. So you would take a little snippet of audio that was the word one. And you would look for in your test audio where that piece of audio matched well. And so that was a template matching algorithm. There were some extensions on that. Dynamic time warp was one of the big ones that basically let you match those two segments even if they were different lengths. And that ends up being important because, as you heard in that something example, sometimes you can say it really quickly, and sometimes you can say it really slowly. And so the length of time that a word takes changes. Dynamic time warp adjusted that. HMMs replaced dynamic time warp with a more generic method. At the time, they were generally coupled with so if you remember back to the HMM discussion, it's basically a Bayes net. You have your transition probabilities and you have your emission probabilities. The emission is the evidence telling you what the state is. Back then, until just about 5 or 6 years ago, most people used what are called Gaussian mixture models for the emission probabilities. So that was the most popular one. These days, we use neural nets. So as these techniques developed, we also made the speech recognizers be able to perform more general tasks and more accurately. So we started with just single words. So for example, you might have just recognizing digits. So the only thing it would recognize is, did you say 1 or did you say 7? Not continuous. So I can't say 1, 7. I have to say 1 or 7. And you can't say anything. You just have to limit it to a small vocabulary. Generally, these were in highly controlled acoustic environments, no background noise, with a mic right next to your mouth, so that there weren't any echoes and these other effects didn't happen. And actually, even on some of these early techniques, that worked. But it's just too limited. You can't do very much with it. Later on, with the template matching and dynamic time warp, you started to do short phrases. And so this is sort of command and control. So I could say open email. And the number of phrases it would recognize was small, but at least it wasn't a single word. But it was still, you had to have very clean acoustics. And then later on, as we started developing these methods with HMMs, GMMs, and neural networks, we were able to do continuous speech, like I'm talking now, with the strings of words all together. The vocabulary size got bigger and bigger, so we started with sort of a 10,000 word vocabulary, and then a 20,000, then a 60,000, then 120,000. And I'll talk, if I have time at the end, I might talk a little bit about how weird that is in some other languages where the vocabularies can be very, very large. The grammar complexity went up. So if you think about controlling your cell phone, there aren't a lot of things you can say to it. As I said, you can say, open my email, open the email from person. That's the grammar, where you limit what can be said sort of using a formal language. And you might learn more about that if you ever take a programming languages class or a compilers class. As time went on, those got more and more complex. If you want to recognize stuff like I'm saying, the grammar is a little different. It's statistical. In other words, you try to be able to recognize everything, but not everything with the same probabilities. And I'll talk about that more in a bit. And as I said, you get increasingly difficult acoustic environments. So where I was, we did one of the first recordings of actual meetings in a real meeting room with just a microphone on the table. And that's remarkably hard. Even with the best systems in the world, you sort of get 40% of the words wrong if you're just recording with a microphone on the middle of the table with no other additional processing. So speech recognition, as I said, goes back 120, 130 years. There's way too much for me to talk about in the time we have. So here's some of the highlights of the stuff I'm not going to talk about. This is mostly sort of modern stuff. There's huge amounts of history that I'm not going to talk about. And I actually, I recommend if you're a researcher in the field to get to know that because everything is cyclic. Stuff comes back again. I'm a firm believer that we should be hiring linguists because the idea that language has no structure is ridiculous. Of course it has structure. We just have to learn to exploit it correctly. But at any rate, so one of the big things I'm not going to talk about is an alternate way of doing speech recognition that's become popular called connectionist temporal classification, CTC. And this is a method of just using one big neural net. It's called a recurrent neural net. It's different than what we've learned a little bit. The algorithms are actually the same, but it has this little trick where you're trying to do a sequence of inputs instead of just one input. Right? So right now, what you guys have done is, for example, with a digit recognizer, written digit recognizer, you get one image in, and you get one answer out. Speech recognition is you get a series of acoustic information in, and you want one answer out, what word it is. And the recurrent neural net uses a little trick where you sort of copy one of the hidden unit values back to the input. And then you give it the next frame, and you copy the hidden values back to the input. So you have this recurrence going on that copies the different earlier time steps back into your net so you can learn temporal patterns. CTC has a little more to it than that, but it's basically a method of not doing any of the stuff I'm going to say in the rest of the lecture and just using one enormous neural net to do everything. And I find that really slick from a conceptual viewpoint, but at least right now it's computationally very expensive because the nets are gigantic, and it's not currently as accurate as the methods I'm going to give right now, what I'm going to talk about. So we'll get to a moment what I am going to talk about, but I'm not going to talk about CTC, but it is an area of current active research, and it's really cool. So I don't want to give it a bad rap. It's just don't have time. Language modeling is another really big topic, and I had to cut something for this talk, and so this is what had to go. You got a taste of it for those of you who took midterm 2, midterm 2, with the Pacmanian language modeling. That is language modeling. It's figuring out what the probability of a particular utterance is given a bunch of training data. This is really important in speech recognition, because otherwise you get recognize speech rather than recognize speech. And you get that weird string of my, num, burr. The language model is what saves you from that, because those other sentences are very improbable. People don't say them. And so you need the language model to account for that, but I'm not going to talk about it because there's no time. There's tons of uses of ASR, of automatic speech recognition, on what you would actually do with it. And this matters because you would optimize different things depending on what your application is. So, for example, when you're talking to, the Google's Cortana? No, that's Microsoft. Whatever Google's one is. You're usually doing search. And you might want to optimize things very differently if you're doing search than if you're trying to transcribe a lecture. But I'm not going to talk about that. I'm just going to talk about trying to get the words right and treating all the words equally. So I treat a mistake in saying instead of the exactly the same as saying Josh instead of encyclopedia. So obviously in a real application you wouldn't want to do that, but there's too many different applications. And so typically in the speech recognition community, you just count how many words are right versus how many are wrong. And then there are just tons and tons and tons of details, complications, and edge cases that I'm not going to talk about. Basically, every slide I'm going to show probably has 10 theses and 1,000 papers behind it. It's a big field. There's been a lot of research. There's a lot of lore. I've simplified a lot of the stuff I'm going to show on the slides for pedagogic reasons, but real systems are much more complex. I think we'll probably have time at the end for me to go through some of those, but just be aware that there are, just as I said, lots and lots of other things you can talk about. So what I am going to talk about is the current publicly available state-of-the-art system. And by publicly available, I do mean open source. So there are a bunch of closed-source speech recognizers where we don't really know what they do. Some of them are a little better than the ones I'm going to talk about, but not by a lot. Most of them use methods that these packages use. And so Caldi is the big one, big open source. You can't just download it and run speech recognition. It's a toolkit, not an end-user platform, but it sort of implements everything you might want to implement for doing speech recognition. HTK, which is called the Hidden Markov Model Toolkit, the name gives away the fact that it's much older. It's incorporated newer methods, but it's just an older code base. And I think Caldi at this point has more critical mass. Its licensing is a little more lenient. The neural networks for acoustic modeling, the acoustic modeling is what's the emission probabilities, and I'll go into that in more detail. But there is a huge neural net component buried in all of this for figuring out the acoustic models. And there are lots of toolkits for that. You know, if you came to my office hours, I talked a little bit about that. Caldi ships with several built into it. They're pretty specific to speech. You could use them for other things, but it might be a little bit of work. Keras, TensorFlow, Theano, many, many others you could use for this component. One of the underlying data structures is called a weighted finite state transducer, which, again, I'll talk about more in a little bit. There's, once again, an open source package called OpenFST that handles these. This is something that you would learn, again, in a compiler's course or a programming languages course. And I'll talk a little bit about it, but there's lots of depth that you could go through, more than what I'm going to say. Okay, so that's sort of the background material. Any questions on that before I go on anything I've said so far? Okay, so what I want to talk about now is actually what is audio. Okay, so I'm talking, sound waves are coming out of my mouth. A sound wave is a pressure wave in the air. So it displaces forward, and just because of physics, it bounces back, and you get back and forth, back and forth, back and forth. And that's what sound is. And it travels from my mouth through the air. The air modifies it a little bit. As I said, it bounces up and down. But basically, it goes from my mouth into your ear. And you can see in the diagram here, I have a little box around the first component that it hits, called the tympanic membrane, or the eardrum. So the eardrum is just a membrane that moves back and forth as the air pushes against it, back and forth, back and forth, back and forth. It does it very, very quickly. And then it's connected to the next component, but it passes that in basically as a signal. And so this is what the signal looks like, right? So this is me saying, this is an example of me talking. And this, what you're seeing on the screen here, is the result from a microphone. But the microphone also has that little membrane in it that goes back and forth, and it's basically telling you how far displaced is that membrane, up or down. And again, just because of physics, if you push it real hard that way, it's a spring and it wants to bounce back, so it's always going to average to 0. So here's the same thing, just zoomed in a bunch, for me just saying the word this. And you can say there's a lot of structure in this. There's a lot of structure in this. But it's sort of hard to pick out. And so although you could pass this directly into your machine learner, that's not typically what we do. So this is what the microphone signal looks like. It's also what the tympanic membrane looks like. But usually what we do is we go to the next component down in the ear. And this is called the cochlea. And so this is the tympanic membrane sends the signal to the cochlea. It looks like a little snail. And the cochlea has tiny little hair cells in it of different sizes. And just like a guitar or a violin or a piano, the thin ones vibrate faster than the thick ones. And so the thin ones respond to high frequencies. The thick ones respond to low frequencies. And there are a whole bunch of these that are coiled up into the air, tens of thousands of them. And each one responds to a different frequency. And so what that looks like from a computer science processing point of view is a spectrogram. And so that's what it looks like. So this is the same sentence. This is me. This is an example of me talking. Once again, it's time on the horizontal axis. But this time it's frequency on the vertical axis. So the vertical axis is how much is each hair cell in the cochlea responding to the signal. And so at the bottom is low frequencies, and at the top is high frequencies, and audio is just made up of low frequencies and high frequencies in exactly this way. So, the white is the highest energy of that particular area. So when I say this, there's a bunch of energy sort of in a couple of different clumps. And you can just sort of see as you go along how it changes. Now, this looks much more reasonable. This looks like something we could actually do something with, because there are patterns in here that you can sort of make out and do correspondences between the sounds and what the spectrogram looks like. Okay? Any questions on that? Go ahead. The original one? That? Yeah, because just from a human point of view, no matter how much I look at that, I can't figure out what the sound is. Right? So that's one answer, that there's just too much variety. It's too dependent on how loud you're talking, right? Because how loud you're talking is how high it's going to be. And so if I start talking quietly and then I start talking louder, it's hard to tell the difference between that and just different speech sounds. Whereas in this one, as I said, I can start to see patterns in this, right? So if you look, I got to point at the screen, sorry for webcast viewers, but sort of to the left here, there's a little area where the red is going up. And that is, symptomatic of a particular speech sound. So if you asked a linguist, actually if you take the linguistics, phonology, and phonetics class, you'll be given these and you'll be asked, what did the person say? And you can figure that out with a little bit of practice. It's not that hard. Whereas on this signal, it's very, very hard. Another answer to that is just that this is the signal the brain gets. The brain doesn't get that first signal. Right? The first signal is the tympanic membrane to the cochlea. The cochlea then sends us to the higher levels of processing in the brain. And what we found just historically is, especially for things like speech evolved to be understandable by humans. It co-evolved. Production and understanding co-evolved. And so it's worthwhile to be influenced by the ways humans do it. You're just going to get better accuracy. I think at the end of the day, the real answer is because this way is more accurate. There are people who advocate the first way. Right now, it's not as accurate. And in my opinion, it's always going to be fragile compared to this because certain types of interference, noise interference, like volume, just like I mentioned before, don't show up in the first. In this one, do show up in the first. it's exactly the same number of features. And so we'll talk about features in a second, but it is a good question. So the way you mechanically transform between the two, it's not the way the ear does it, but the way we do it on a computer is with a Fourier transform. Have people done Fourier transforms? Does people know what that is? Okay. So you know that when you do a Fourier transform, it's the same amount of information. It's just one's a spectral representation and one's a temporal one. And so that's what this is. This is a short-term Fourier transform of the original signal. So you could just use this, but this still has a big problem in that if we're sampling audio, we typically do it at 44,000 samples a second. You may have heard of that, like for CDs, 44 kilohertz recording from music. There's not a lot of information above 16 kilohertz in audio, in speech rather, but nonetheless, you still have a lot of data. And so there are 44,000 of these little vertical lines every second. And that's much, much faster than my articulators, my mouth and my lips and my tongue can move. And so the rate of change of what I am saying is much slower than 44 kilohertz. It's about 100 hertz. In other words, the difference in the signal in my speech only changes about 100 times a second, not 44,000 times a second. So that's another problem, that this is actually too dense with information. You can handle that, but it's computationally expensive, and generally it's better to compute more cooked features, more processed features on this. And so that's the next slide. And so here is an example of one feature. If you wanted to take this whole audio signal and represent it as one number, you could just take a box and say, what is the total amount of energy in that box? In other words, the color is representing how much energy is it. You just sum up all those values in the box, and you get a number. And that would represent one feature at that time, right? It turns out that humans are less sensitive to high frequencies than low frequencies. In other words, we can tell the difference between two low frequencies easier than we can tell the difference between two high frequencies. And so what we typically will do is, when we're computing features, we'll make them different sizes. So at low frequencies, they're spaced pretty close together. At high frequencies, they're spaced pretty far apart. In the example here, I'm just showing typically we do 8 or 13 or 20 or something like that. But it's something like this. And so this represents one feature at one time slice. So if the width of that were 10 milliseconds, you'd get 100 of these per second. And so you would get 4 numbers every 10 milliseconds. Or as I said, 13 or 20 or however many boxes you actually do. So usually we're sampling it uniformly, as I said, at 10 milliseconds or 100 per second. And we call that a frame. It's just a unit of time. So instead of calling it 10 milliseconds, you'll call it a frame. And we break the whole thing into that. So these are the features that I would use for this audio file. For the file of me saying, this is an example of me talking, I would break it up into these number of features. One vertical column for each frame. And this is actually more like what the brain what gets sent to the higher levels of the brain, these sorts of features. They're tonotopic, in other words, they're based on the tone, and they have this different spacing. It's not linear. The scale is called the Mel scale. That was derived from actual perceptions. Any questions on that? Okay. So I should say that at this point, you now actually have enough to run some algorithms that you've already learned, right? You know what the features are. I give you a label, and you can do some matching. So let's start with an easy one, which is, let's say you have training data and they're audio files, and you break them up just as I said so that you get a set of features. And I tell you there's just one word in it. And I ask you to write a classifier to tell me whether the word is 1 or 0. Nothing else. That's all I want to know. Is it 1 or 0? Here are your features. So what algorithm that you already know could you use to solve this, given that you had plenty of training data? So I'll let you think about that for, 30 seconds. Chat among yourselves about what you think might be a good algorithm. I'll give you another hint. You should have done it already, I believe. My final hint. Okay, my final hint should have given it away. You could just use naive Bayes. So the same way that we use naive Bayes to solve the written digits, you could use it to solve this problem as well. You have a set of data. You have a set of labels. You do some counts on how many times the label occurs, how many times the feature occurs for the particular label you're interested in. So you could use naive Bayes if you have enough data. So my question is, why would this be terrible if you didn't have a huge amount of data? Now, this is a little tricky. I'm not really talking about just accuracy issues. There's something intrinsically different about the speech signal of me saying 1 or 0 versus me writing it down on an 8 pixel by 8 pixel grid. And so maybe I'll give you the hint and then let you think about it. How many features are there in the audio file? Think about my something example. Right? That would be my training data. How many features are in each of those audio files? So let me go back. So here are the features for the audio file. This is an example of me talking. Let's say it were a different audio file. How many features would it have? Smaller number if it's shorter, bigger number if it's longer. So each audio file has a different number of features in it. So if you were trying to train a naive Bayes method, the only training data you could use is training data that had exactly the same length as the segment you're trying to test. Right? So yes, you could do it, but you'd need huge amounts of training data because you couldn't use, if it was 102 frames, how do you compare something that's 102 frames long with something that's 101 frames long? I don't know. There are lots of different methods of doing it, but naive Bayes isn't one of them. Right? So you just need tons of data to do naive Bayes. So let's start building up how you would actually do it, or maybe I should say how you do it with the systems we're currently using. So what we start is with what's called a pronunciation dictionary, or a pronunciation model. This one is a publicly available one called the CMU Dict. And, if you've ever looked up how to pronounce words in a dictionary, this is sort of similar. It's a particular phone set on the right here. So you can see the top line is zero, and and so on. And this is just publicly available. Someone gives it to you. And now we have the pronunciation for each word. So we're breaking the word into smaller pieces. And this is going to help us solve the problem. So instead of trying to solve it on the entire word, we're going to try to solve it on just subcomponents. And actually, for the next little bit, I don't think I mentioned this, I'm only going to be talking about recognizing a single digit in an audio file, where the audio file has one word in it, and it's either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay? So that's pronunciation dictionary. Any questions? Go ahead.
So you're still dealing with features, right? Originally, before you
Correct. Correct.
So does this dictionary just resolve these features for you, like their proper subclasses?
We'll get to that in a moment. So even these subcomponents have exactly the same problem, that the amount of time you spend in each of these phonemes can vary. Right? So I can say 0, or I can say 0, and it's the same word. I can say 0, and it's the same word as 0. So all this is doing is sort of chipping away at it. We haven't actually gotten to the solution yet. That's the next slide. So here's the solution. Okay, so we're going to show this, and then we're going to say, you know what? That's too scary. That's too hard to understand, just draw. So I'm going to show a slightly different one that we've seen before. So instead of saying that this is wu followed by followed by n, one, the word one, I'm going to say this is clear weather followed by cloudy weather followed by rainy weather. This is an example we've seen before in the HMM lectures. And so basically this is modeling, saying that it's clear for a few days, then it's cloudy for a few days, and then it's rainy for a few days. It's a little different than the examples we saw before because I put the labels on the arcs rather than on the nodes. And that's just how they do it in speech recognition. It's encoding the same information. And if you go back to the HMM lectures, you'll see that this is called the transition graph. This is telling you how the weather changes each day. So on day 0, it can either be, this model is saying it can either be clear or cloudy. And if day 0 is cloudy, then you get to the next day, or the next state rather, and then it can be cloudy for a while, for more than one day. Right? So this is the transition diagram. This tells you how it evolves in time. This is not saying that it's 3 days long. This can be any number of days long. This is just telling you how you transition from one to the other. So again, if you go back to the HMM lecture, you'll see that this is one of the representations for the conditional probability tables of a Markov chain. That's all the words together. But all it's really saying is that it's clear for a few days, then it's cloudy for a few days, and then it's rainy for a few days. The double circle around the last one is just saying that that's the end state. That's where we're saying we end. And so if we have a sequence of days and we're wanting to see how probable that sequence of days is, we go until we hit that final state and we're at the end time. Okay? So the question, so I have a couple questions here. How many days does this represent? Is there a minimum number of days this can represent? Is there a maximum number of days this can represent? Go ahead.
There's a minimum, so but maximum is
Correct. Absolutely correct. So there's a minimum number. In order to get to the end state, you have to at least go from state 0, see that it's cloudy, go to state 1, see that it's rainy, go to state 2. So basically, we've consumed 2 days, two days to get to the end state. We've consumed a cloudy day and a rainy day to get to the end state. But we also could have gone clear, 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 cloudy, rainy. And we're at the end state as well. So this is the transition diagram. It's not the Bayes net. So the Bayes net for this is a Markov chain. And to construct the Bayes net, you have to know how many days you're talking about. So here's the Bayes net for n days of weather. All right, so the top one tells you what the conditional probability tables are. It tells you when you're going from W1 to W2 what the probabilities are. I didn't write them, but there would be little labels on each of those arcs telling you what the probabilities are of going from one state to the other. So we might say that if you're in state number 1, there's a 50% chance of it being cloudy and a 50% chance of it being rainy. If you're in state 0, maybe there's a 25% chance of it being cloudy and a 75% chance of it being clear. Right, so I'm hoping this is all pretty familiar. Okay, is that clear? So there's some conditional probability tables I haven't shown, but the relationship between these two should be clear, that the first one encodes would be another way of encoding what the conditional probability tables are for this Markov chain. Now we want to go one step further, which is, let's say, we're in the mean advisor example that we gave before, where you're in a basement room, you never get to see what the weather is. All you get to see is whether your advisor is carrying an umbrella or not, or let's say all you have is a temperature gauge. So what that looks like is a hidden Markov model, right? So the transition graph stays the same. The transition graph is just telling you how it evolves in time. It's not telling you anything about any other additional evidence nodes. So this is the hidden Markov model that's equivalent to the example that we gave before about the grad student who doesn't get a window. Once again, you have n days of weather, and now you have n observations that you could have seen of, let's say, a temperature gauge and a humidity gauge. And, we know how to do inference on this, right? This is something we've learned. But, again, the transition graph hasn't changed. The transition graph tells you how the weather is evolving. It doesn't tell you anything about your evidence variables. And so, again, from a Bayes net point of view, we have two types of conditional probability tables in this. One is the transition conditional probability table. That's the probability of going from one state to another, from cloudy to rainy or from clear to cloudy. And those are the arrows between the W's, would be where that conditional probability table lives. We also have an emission conditional probability table, which is between the W's and the E's, the evidence. So this is telling you what's the probability that it's clear given that the temperature is 40 degrees and the humidity is 95%. Okay? Again, this should all be review. The emission probabilities, someone could give you, the probability fairy could give you them, or you could have some function that computes it. The function could be a big, complicated neural net, where the input is what the evidence is, and the output is the probability of each weather condition. So that's something to remember, that the emission probability, again, is separate from the transition graph. Okay, any questions on that before we go back to the speech example? So I'm hoping that this is abundantly clear because we've covered it before. So now all I'm going to change is we're going to do one, instead of clear, cloudy, and rainy. It's the only difference, plus a little notation difference. I've changed the W's to Q's, and I've changed the E's to X's. I've done that just because this is the notation that's in the speech recognition literature. And so you should be familiar with it. The Q's represent the states, once again. What are those? Well, they're just like in the previous example, the states were cloudy, clear, and rainy. The states in this one are the W sound, the sound, and the N sound. Those are the states. But everything else is equivalent. We have a transition graph, which tells you how the states evolve over time, and we have emission probabilities that tell you, given your evidence, which in this case is the features that we did right at the beginning, towards a few slides back, given those features, what's the probability that it's a W sound versus an sound versus an N sound? So I'm hoping you see that we've now resolved the length issue. This is a model for how you say the word one. The model is I say wu for a while, then I say for a while, and then I say n for a while. Just like before, the model was it's clear for a while, then it's cloudy for a while, and then it's rainy for a while. Okay? Now, we know how to do inference on this. So if I gave you all the conditional probability tables represented by this HMM, what would you use to compute the probability that the person said one, right? That they really said wu, n, given the acoustic features. In other words, what algorithm would you use to compute that conditional probability? Does anyone remember the name of it? I'm being a little fast and loose, so you might not remember it even if you look at the slides, because this is actually a slightly modified version of the forward algorithm. Right? So this is something we learned in the HMM, that there's an algorithm that says what's the probability, the conditional probability of the normal forward algorithm is of the probability of Qn given all the evidence. But with a little modification, you can do the whole thing. And this tells you what is the probability that the person said one given the evidence. Right? This doesn't tell you how long they said wu or n. It just tells you what's the probability of one, just like that statement says, for a particular utterance that you give it of length n. Is that clear? Okay, so given that, how about this question? If I gave you, again, all the conditional probability tables, what algorithm would you actually use to compute how long they said right? The transition matrix says they said for some amount of time. I want to find out what's the most likely sequence that matches the word one, and how long were they saying in that most likely sequence. Does anyone remember the name of that algorithm? Viterbi, very good. So the Viterbi algorithm would tell you basically how long you stayed in each state. And that's going to become important later. So basically now we have a whole bunch of machinery in place. So we actually now have enough machinery that if I gave you the conditional probability tables, in other words, a big neural net that could compute the conditional probability tables, you could now do isolated word recognition. And here's how you would do it. Here's the transition network for the word one, the word two, and the word three. Just composed absolutely mechanically using the dictionary. And imagine we had those for, 0 through 9. We also have an algorithm that tells you the probability that the word was one, given the evidence. Using exactly the same algorithm, but, different conditional probability tables, you can compute the probability that's 2, the probability that's 3, and so on. So you run an HMM for every word in your dictionary. Now, again, remember, Although these have different number of states, there are 3 states in that, 2 states in that, and 1 state in that. The actual BaseNet, the HMM, has however many states there are in the actual utterance, right? So if there are n frames in the utterance, the BaseNet that represents this has n frames in it. And so again, we've handled the length problem through this modeling. So we run an HMM on each word, and we pick the one with the highest probability. And we're done. So this is how you run an isolated word recognizer. Now, there are a couple problems with this. The first is scalability. So as I said, for this you would run 10 HMMs. In a real speech recognition system, you typically have about 100,000 words in your vocabulary, so you'd have to run 100,000 of them. That's pretty expensive. There's also a lot of repeated work if you do it this way. So numbers are actually interesting in English because there's not a lot of repeated phone patterns in numbers. And the theory in linguistics is that that's developed to make numbers really easy to distinguish. But nonetheless, you have the t in 2 and the t in 10 are the same sound. And so you're actually replicating a lot of work if you just run each of these separately. And we'll talk about it in a moment. Now, of course, sentences have more than one word. I've just told you how you would run this if you wanted to do isolated word recognition, but we want to do continuous word recognition. And so we need to do that too. And I haven't told you how you actually compute the conditional probability tables. I've given you lots of hints about that, but we haven't gone into details yet. So let's address each one of these one at a time. So the first is scalability. And for the scalability issue, basically it's about avoiding repeated work. And so, as I said, you build a graph for each word. Here's 2 and 10. And basically what you want to do is combine these graphs where you can. And there's a ton of theory behind this. This is an interesting field. As I said, weighted finite state transducers. You'd learn about it in a compiler's class. From a practical viewpoint, there's a wonderful open source toolkit called OpenFST that basically does all this for you. So there's an algorithm in OpenFST that says compose these two things. Or actually, compose is the wrong word. Disjoint of these two things, which is do 10 or 2. And it just does it, and that's what it does. So this is what I mean by avoiding repeated work. So let's look at it again. You have 2 HMMs, one for 2 and one for 10, and you combine them. Now you have one HMM that represents both of them. Okay? Now there's a little wrinkle in this, which is how do you know which word was actually said? If we just ran inference on this thing, it would tell you what's the probability that they said either 10 or 2. We don't want that. We want to say, was it 10 or was it 2? Well, you can see from this graph that if you end up in state 1 in the upper right, then they said 2. And if you ended up in state 3 with the n on the lower right, they said 10. There's a particular way of representing that. And this is just a notation. And again, it's deeper than I'm going to give because I'm not going to talk about the theory of weighted finite state transducers. But from our point of view, the arcs now have 2 things on them. What I've shown already, which is the input and also the output. And so basically what you think about it is as you traverse this graph, you consume the inputs and you emit the outputs. Right? And then there's an additional symbol here, epsilon, which on the input means don't consume any of the input. On the output means don't output anything. And so look at the graph on the right here. It's basically equivalent to the graph on the left, but I've added the output notations to tell you which word it was. And you have to stare at it a little bit and think about transitioning through this whole graph, about how you would do that. You're in t for a little while, then you're in for a little while for 2, and you're in t and then and then n for a little while for 10, and then you exit to state 2, which is just an exit state. And basically, if you traverse this graph all the way to the exit state, you will have consumed all the input, and you will have output one word. Okay? Any questions on that? Okay, so the next slide is going to show a bigger example. And so this is just an example of combining bad, badge, bag, bid, big, bud, budge, and bug into one big graph. Now, I've used letters rather than phonemes because I know people aren't as familiar. It's easier to read the graph with letters in it. In the real case, you would do it with the pronunciations, not the letters. And once again, the process to generate this is fully automated once you have the pronunciations. It's a little computationally expensive, but not horrendous, and you only have to do it once to assemble a data structure. And the data structure that you're assembling is called a decode graph. Okay? So here it is in all its glory. Bad, badge, bag, bid, big, bud, budge, bug. I can say, if I'm saying the word badge, I can say B for a while, then A for a while, then D for a little while, then G for a little while, then E for a little while. You have to stare at a little while to understand that this graph really is representing that, because there was a lot of automated processing to make this graph as small as possible. And so, for example, if you look at the word budge, and so, again, sorry, webcast viewers, I'm pointing towards the middle top of the image where there's a G colon budge edge. So let's say I'm saying the word budge. Let's follow the graph, how I would have had to do that. I'd start at state 0. I'd say go to state 1. I'd say B for a little while, stay in state 1. Now I've said U, so I go to state 2. And I say U for a little while. Then I say D, I go to state 5. And then I say D for a little while. Then I see the G, and I go to state 9, and I output the word budge. Now, why did I do that? Why didn't I wait to the end to output it? Do you see why? Because there's no other way that you could have, there's no other word you could have produced. So this is the earliest you absolutely know that you said the word budge. You still have to consume some more input, but you know it was budge. There's nothing else that they could have said. Because there's no other word that starts B-U-D-G. Right? And then you say G for a little while, and then you go through some epsilon transitions which don't do anything, and then you reach the end of the word, end of the utterance. Okay? This is worthwhile going back and staring at, because this is sort of the key data structure in modern speech recognition systems. And this is just for, a handful of words. The real data structure has 100,000 words in it. The graph is really big. But nonetheless, it's the same thing. It's a model for how you can say every word in your vocabulary. Is that clear? Any questions on that? Okay, so here's another question, Goat. So this is inferencing on the decode graph. So I got to do a little caveat here because I think I got this a little wrong in my first bullet, saying summing over all legal paths in the search tree would yield the probability that it contained any of the words. Got to be a little careful with this, because what I mean by that is any legal path is any path that actually goes to an output node. So the only output node here is the one at the end. Actually, maybe I should do that here. 10 is the output node. And it's only an output node if you've actually consumed all the input. Right? So you actually have to be at the end of the utterance, the end of the audio file, in the final frame, in order to say, I'm done. Because otherwise you haven't accounted for all the audio. And so, but if you actually do that, and you pick every path that goes to a legal output, and you sum all over them, it would tell you, is it the probability that's bad, badge, big, whatever all those were, if it's any of those. But that's not what we want. We want to know what they actually said. So how would you tell what word was actually there? So this is the question, Goat. So cast your mind back all the way to the beginning of the term, and can you see what algorithm you would use to figure out what word was actually said? And then I'll let you talk about it for a few seconds, and then I'll give you a hint. So I heard a minimax. Does anyone have any counter to minimax? So I will say the minimax is when you don't have all the information. And right at the beginning of the algorithm, you have all the conditional probability tables. You have everything. So you don't need minimax. Any other? So I'll give another hint. Let's say this were a map of Romania. Right? So let's say these were cities. You could use a search algorithm. A* would be one, right? So it's a little different than the map of Romania because we have these self loops. It's telling you could stay in the same city, right? That's a little different than Romania, and it might be best to stay in the same city. It's also a little different because of these weird exit nodes. You're not trying to get to where are you trying to get to in the map of Romania? Does anyone remember? Wherever you're trying to get to in Romania. Bucharest. You're not trying to get to Bucharest. You're trying to get to that end city when you're done with all your input. And also, your conditional probability table give you your scores. Right? In the map of Bucharest, it's just the distance between cities along the roads. In this case, you have to run a neural net to say what's the probability of the particular speech sound you're talking about. Is it ooh at the particular time? So yes, it's a search algorithm. It's a really so we cover everything in speech recognition. It's pretty cool. So someone said A star, and that's absolutely where you were the correct answer, and that would be your go-to. Turns out that's not what we do, and there are a couple of reasons for that. One is that the heuristic is hard to find. So people have tried different heuristics, and really the only ones that have been successful is to run a simpler speech recognition system first and use its output as a heuristic. That ends up being expensive and complicated, and so typically we don't do that. More importantly, for any real speech recognition system, you don't want just the best path. You actually want, the N best. So you don't want to just know what was it big, but what's the probability that it was big, and also what's the probability that it was the second best word? What's the probability that it was the third best word? It turns out for most applications, that's what you actually need, not just the one best. And so we end up, believe it or not, using breadth-first search. It's sort of the last search algorithm you would expect us to use. We've maligned it so much through the beginning of the class, but that's what we use. There are a couple of reasons for that. If you think about how the breadth-first search progresses in that graph, it's doing one time step at a time. That's what a breadth-first search would do in that big graph we did before. And that's nice because as new data gets in, you do a new step in your algorithm. And as you get more data, you do another step. More importantly, as I said, we want these n-best lists. And generally, you can only compose those n-best if you do some sort of breadth first, because otherwise you'll have skipped lots of likely ones. Now, breadth first is maligned because there are lots of problems with it. And the way we get around it in terms of tractability, because this graph is gigantic, and so a breadth first search through it is really, really expensive. And so what we do is, if you remember what the algorithm for breadth first search is you have a fringe that you're keeping track of, and at every step in the tree, you try to expand the ones that are shallowest in the tree. Not in the graph, in the actual tree that you're implicitly expanding. And so all we do is we prune some of those. So what we take is, you take your huge fringe, and you say, well, this is the best one so far. Any that are too far from that best one, you just remove from your fringe, and you don't even pursue it anymore. And that's called pruning. And this is what makes the problem tractable. Most real problems have something like this in it, where you're doing some pruning step. You do it at each step. And you should think about, and you can stare at that previous graph if you want, about why this is not complete or optimal. So if you actually prune, you could remove the very path that eventually is going to turn out to be the best path. So it's not complete. You could end up with no solution at all. That's, the error message in your speech recognizer will be no backtrace to word or something like that, if that happens. And it's also not optimal. So you might have pruned off something where you might still reach the correct solution, but it may not be the optimal one. In other words, you may find a solution that was in for 3 frames, but the optimal one was only 1 frame. But it does make it tractable. Okay, so this is basically how we make the problem tractable. In other words, I've now told you how, given even a big dictionary, you could tell what word was in the input file. But I've only told you how to do one word. So what we're next going to talk about, maybe I should say, are there any questions on that before we go on? Okay. So, but what if the file contains more than one word, right? I'm talking continuously, and you want to know the entire sequence of what I'm saying, not just one word at a time. And as I said at the beginning, there aren't any boundaries between words, and so you can't just break at a space or something like that. You actually have to do a search, just like we did in the previous one. So imagine that I have an audio file, and we're going to stick with our big bad badge example. And what is actually in the audio file is someone saying big bad badge bud bug. Bug bud. Big bad, yeah. Whatever I wrote down there, that's what they said. So how would you actually do that? So this is very complex, so you want to really pay attention to this next slide. So this is if it's just one word. And so we're going to go through a very complex algorithm on how you do it for multiple words. You ready? There you go. Should I do it again? Was that too complicated, too fast? So that's it. That's how you do continuous speech recognition. So if I do a search through this graph, I can reach the end, but then I can go back to the beginning again and look for the next word. And I don't stop doing that until I'm at node 10, state 10, and I'm at the end of the audio file. I've accounted for all the audio, and I've accounted for every word. Just do a search through that. Okay, now that was glib, right? So it was funny, but it was glib. In the real case, not all sentences have the same probability. What I just showed you there is that regardless of what was earlier in the sentence, each of those words has the same probability. And that's just not true, right? In the real case, we have a language model, which says that my example always is if I say the cat, is the next word refrigerator? No. The next word is or was or on, and they're just probabilities of that. And my glib example doesn't account for that. But it turns out that, first of all, you can compute the language model just like I did in the midterm 2 problem. So if you didn't take midterm 2 or you didn't understand this problem, it's worthwhile to at least look at it with the solutions to understand what language modeling is like. And it turns out that there's an algorithm that lets you encode that in a mechanical way. So once you've actually computed these language models in the very way that I showed in that question, there's a mechanical way to incorporate them into the decode graph, which I'm not going to go through. It makes the decode graph even bigger than it already is. So the decode graph is really, really big. But it incorporates the language model, and it's still just the same search algorithm, just with different scores where you've incorporated the language model also. And again, there's lots of interesting stuff on that we don't have time to cover. Okay, so the next question is, well, again, I keep forgetting to ask. Any questions on this before we go on? On continuous? Go ahead. Absolutely. So an easy parallel algorithm is to go all the way back to the first example I gave, where you're running each word separately. And that's very easy to do. And you can do a loop on that, just like we did a loop in this one, to consider all of them. And that works really, really well if you have a small vocabulary. But the bigger your vocabulary, the more advantage you have on doing this complex graph instead. And this complex graph is hard to parallelize. So you can do it, but every time you have sort of multiple arrows going into one node, you have to resolve a data structure. And that's complicated. You can do it, but it's not easy. So basically, it's active work on how you parallelize the search part of this. Now, what we're going to get to next is how you compute the conditional probability tables. That's very parallelizable. And that's typically the computational bottleneck, is actually computing the conditional probability tables rather than doing the search. Well, I shouldn't say that. Nowadays, the search is the computational bottleneck because we've already parallelized all the other stuff. And so we have the normal Amdahl's law that, we parallelize the conditional probability table computations. And so now the search is the bottleneck. Anything else? Okay, so now let's actually talk about where we get these conditional probability tables. So if you go back and you look at the HMM that we drew before, the conditional probability table we're talking about is the probability of which phoneme is it at a particular time, given the features at that particular time. That is the emission probability that we're looking for. So it's the probability of each phoneme at the time t, given the acoustic features at that time. These are just a set of numbers, one for each phoneme that you have in your system. So, for example, you might say that the probability at time 1 that I said ah is 0.31, and the probability that I said at the same time is 0.01. And you have one of those for each phoneme in your language. So you typically have something like 40 of these at every frame. And you need to compute those. So any machine learning algorithm you can think of could be used to do this. You could use naive Bayes. You could use Gaussian mixture models. These days, everyone uses deep neural nets. And again, remember what the deep neural net does. You have some input features, you have an output class, you train it on data that you already have, and the output's a probability. That's exactly what you're looking for. So that's what the emission probabilities are, is a function which is learned by a machine learning algorithm, which maps your input features into probabilities. The training data are your acoustic features every 10 milliseconds, which we talked about earlier, and then which phoneme was it at every 10 milliseconds. So to train this, we need to know what was the answer at time t equals 1. Was it an ah or was it an r? Okay? So for training, computing the features is generally quite easy. We talked about that before. It can be computationally expensive, but usually not compared to everything else. You just get a set of numbers every time sequence. That's the input to your training of your machine learning. The labels, on the other hand, are much harder to come by because, again, you don't know. If I just tell you the sentence, this is me speaking an example, you don't know how long I was saying the I in this. So there are some corpora where linguists have put on headphones, listened really carefully, and labeled for every 10 millisecond what phoneme it was in. This is really labor-intensive, very hard to get right. There's only a very little amount of data available for it. This is why TIMID is an interesting corpus, because they've done that for a subset of it. But it's not enough data. We really want to train on huge amounts of data, and so you want to be able to do it on where all you have as ground truth is the whole sentence that was actually said, not broken up into how long each word was or how long each phoneme was. So going from the sequence of words to the sequence of phonemes is called forced alignment. Just a technical term for how we actually do it. And again, I talked about this earlier in the single word in the single word example. Now I'll talk about it in the multi-word example. So basically, to do forced alignment, you construct this decode graph with what was actually said. Right? We're talking about the training example, so we know, let's say we have an audio file, and let's say it's 100 frames long, and let's say we know that the person said, big, bad, badge. That's what we know they said. That's what's in my training file example. So we construct a decode graph with just big, bad, badge in it. And that's our whole decode graph. I mean, this looks kind of big, but it's tiny, tiny, tiny compared to anything that they might have said. So all it's encoding is the fact that each phone might be phoneme. I'm sorry, I'm going to always get that wrong. So unless you're a linguist, don't worry about the difference, but I'm going to say phone and phoneme, they're the same thing. Don't worry about it. Unless you're a linguist, and then, you can come up and beat me up after class. But at any rate, you construct this graph, and you run the algorithm exactly the same, right? You still do a search over it. You find out what the most likely sequence is through this. And once you found out what the most likely sequence is, you know how long they stayed in state 2, the I in big. Then you map that back to your audio data, and now you have training data for your emission probabilities. So all you have to do is take what was actually said, run your machine learning, run your speech recognition algorithm on it, and you get training data. Does anyone see the problem? So this will absolutely work, but I introduced a logical a circle in here. Run the normal algorithm. Well, how do we do that if we haven't already trained an algorithm? I've told you you have to, in order to train the algorithm, this is what you have to do. So to train the algorithm, you need an existing algorithm. Well, for an existing algorithm, you have to train it. So you need to bootstrap. Does that make sense? So how do you run the normal algorithm if you haven't already trained it? Well, you have to bootstrap. And so there are a couple different ways of doing it. You can start with an existing system. And so what we used to do is we started with TIMIT, because TIMIT was actually labeled for those tiny, tiny little sequences. And we would train a speech recognition system on TIMIT. And then when we got new corpus, we would run that recognizer on the new corpus to generate a forced alignment, and then run it that way. That doesn't work real well because TIMIT is such a weird thing. She held your suit in greasy wash water all year. It's just not something people say. And the acoustic situation is weird as well. So it doesn't work very well. So usually what you do is what's called a flat start. And so what the flat start says is you take your whole sentence and you break up the audio absolutely equally. You assume every phoneme takes exactly the same amount of time, divided equally along your whole utterance. Obviously, that's a terrible assumption, right? That's absolutely not right. But it turns out to get close enough that you can get a first pass and bootstrap your system. Run a forced alignment using that system, get better labels. Now you have a better system. You can run forced alignment again and get a better system again. And so, in these big state-of-the-art systems, if you actually want to train a new corpus, you might do this 6, 8, 10 times, often with subsequently more and more complex examples as you go. So any questions on that? And so that's basically the whole system. I've told you basically end-to-end how you run a speech recognition system. So the summary of it is that the acoustic features are binned energies from the spectrogram. That's the simple example I gave you. As with everything else in this talk, the actual thing is more complicated than that, and you usually do a lot of additional processing to make it better still. But in the simplest case, it's just think about those boxes in the spectrum as being your features. Your words are decomposed into phonemes using a pronunciation dictionary. You form an HMM from the phonemes with your features as evidence. So your features are at the bottom of that as evidence. Your Markov chain is formed from the phonemes from your pronunciation dictionary. Your language model weights the likely sentences higher than unlikely sentences, and I didn't talk about that very much. But again, it's a purely mechanical method of incorporating it. You throw all of that into a big weighted finite state transducer code and produce this decode graph, which encodes all this information. And basically, it encodes all possible sequences of all pronunciations of all possible words. Right? So it's pretty amazing that this works at all because, that search is just so gigantic. But pruning basically saves you. And lets you actually get something real out of it. And so you do a search through the decode graph, and it gives you the most likely sequence of words. And so if people are interested in further reading, I have 3 recommendations. These are all, I picked people I knew rather than maybe the best books. But so for nuts and bolts, this is a little old. They're coming out with a new edition really shortly. But still for nuts and bolts, it's one of the best. Speech and Language Processing by Jarafsky and Martin. The Gold, Morgan, and Ellis book has a lot of history in it, in addition to sort of broad topics on audio. It covers more stuff than just speech recognition, so if you're interested in audio in general, that's a good book. And then less technical is Roberto's book, The Voice in the Machine. So this is more suitable for a educated lay audience, not necessarily a CS188 audience, more layman than that, and it has a lot of history and interesting stuff as well. And I have, we only have 3 minutes left. I have a bunch of slides on complications that I was not planning to show, but I put them in there so that, webcast or later on you can go through them and just see, the many different complications, axes of active research there are in speech recognition to make the system actually work. The system I've described here, if you actually implemented this system, you might get half the words right, even in a clean, good acoustic situation. You really need to do a lot of these extra stuff to get it to really work. Okay, so we have a couple minutes for questions, and otherwise, happy Thanksgiving. And, I had fun with this class, so again, thank you all very much. And as usual, I'll spend a few minutes outside if anyone wants to chat.